Hello, young physicists. Ever wonder why some atoms just can't sit still and keep breaking apart all by themselves? Well, today we are diving into the fascinating world of radioactivity, where nuclei get spontaneous and throw out tiny pieces like a cosmic fireworks display. Here's a little joke to start us off. Why did the nucleus go to therapy? Because it had too many decay issues. So, what exactly is radioactivity? Simply put, it is the spontaneous emission of radiation from unstable atomic nuclei as they transform into more stable forms. The cool thing is, this process doesn't need any outside push. It's completely random and probabilistic, like waiting for popcorn to pop. You never know exactly when the next kernel will burst. Back in the late 1800s, Henry Becquerel discovered this mysterious energy let loose by uranium sols. Then came Marie and Pierre Curie, who dug deeper and found three types of radiation: alpha, beta, and gamma. Picture that, tiny particles and energetic rays shooting out from inside atoms. Each decay type follows its own unique signature. For example, in alpha decay, the nucleus loses two protons and two neutrons, which we call an alpha particle. This means the original atom, symbolized as X with atomic number Z and mass number A, transforms into another nucleus Y with atomic number 2 less, Z-2, and mass number 4 less, a -4, plus an alpha particle flying away. In notation, it looks like the original nucleus X goes to nucleus Y plus an alpha particle. One surprising fact is that radioactivity does not care about chemistry or physical conditions. Whether the atom is bound up in a compound or under high pressure or temperature, the decay rate remains the same. Radioactivity marches to its own beat. Imagine the diagram showing a nucleus at the center emitting three arrows, one for the alpha particle, which is a slow and heavy helium nucleus, another for the beta particle, a fast electron or positron, and a third for the gamma ray, a burst of high-energy light. This picture helps us visualize how a tiny nucleus can eject these different types of radiation simultaneously or separately. So, to sum up, radioactivity is nature's spontaneous nuclear drama, atoms deciding to rearrange themselves and emit energetic particles or waves, all without needing a nudge from outside. Ready to explore their star trio, alpha, beta, and gamma radiation? Let's go! Alright, team, now that we know what radioactivity is, let's zoom in on the star performers, alpha, beta, and gamma decay. Here's a joke for you. Why did the alpha particle get invited to every party? Because it always drops in with a big positive charge. First up, alpha decay. This happens mainly in heavy nuclei, think uranium or radium, which are just too big and heavy to stay put. They get rid of an alpha particle, which is basically a helium nucleus made of two protons and two neutrons. When it flies off, the original atom loses 2 units from its atomic number and 4 units from its mass number. Mathematically, that's written as the nucleus with atomic number Z and mass number A becoming a new nucleus with Z-2 and a -4 plus an alpha particle. This process lightens the atom and makes it more stable. Next, beta decay. This one's trickier and involves transformation on the subatomic level. A neutron can transform into a proton, emitting an electron called a beta- particle and an antineutrino, or a proton can turn into a neutron, releasing a positron, which is like an anti-electron, along with a neutrino. The key reaction here is a neutron turning into a proton plus an electron plus an anti-electron neutrino. This process changes the atomic number by 1, but the mass number stays the same. Finally, gamma decay. After alpha or beta decay, the daughter nucleus sometimes is left excited, kind of like it just had an energy drink. It then calms down by emitting a gamma ray, which is a high-energy photon, without changing its proton or neutron count. So in notation, excited nucleus X star becomes X plus a gamma photon. Think of gamma rays as the flash of light after a fireworks burst. These decay processes aren't random chaos, they follow strict rules: conservation of energy, momentum, electric charge, and quantum numbers like lepton number, kind of like the universe's referee making sure no rules are broken. Imagine the energy level diagrams here. Before decay, the nucleus is like an excited student ready to jump to a new grade. After decay, it relaxes to a lower energy state, releasing energy as alpha, beta, or gamma radiation depending on the path. So, whenever you think of radioactive decay, remember this trio working like a high-stakes nuclear dance governed by energy and conservation rules, making unstable nuclei peaceful again. Now, let's talk about the countdown clock behind radioactive decay, the law that tells us how fast atoms break down. But first, a fun question: why don't radioactive atoms ever get tired? Because they have half-lives. See what I did there? Here's the essence: the rate at which nuclei decay at any instant is proportional to the number of nuclei still left undecayed at that time. We express this as dN by dt equals minus lambda n, where dN by dt is the rate of change of nuclei number with respect to time, n is the number of undecayed nuclei, and lambda is the decay constant representing the decay probability per unit time. Solving this differential equation gives us a famous exponential law: n of t equals n naught times e to the power of minus lambda t. Here, n naught is the initial number of nuclei at time 0, e is the base of natural logarithms, and t is the elapsed time. This formula tells us that the number of undecayed nuclei falls exponentially as time passes. Lambda, the decay constant, has units of inverse seconds or per second, meaning it tells us the chance a single nucleus will decay every second. A larger lambda means faster decay. This law isn't just about numbers, it introduces us to key concepts like half-life and mean life, which tell us how long it takes for atoms to lose half their population or the average lifespan of a nucleus. Picture the diagram showing a curve falling steeply at first and then leveling off, illustrating exponential decay. On the left, we see a straight line in a logarithmic plot, confirming the mathematical nature of decay. So, this law neatly summarizes the seemingly chaotic decay into a predictable, smooth mathematical dance, telling us how the ticking nuclear clock runs. Continuing our decay adventure, let's decode two important timers that nuclear physicists love: half-life and mean life. Here is some physics humor. Why was the radioactive atom always calm? Because it knew half of its worries would disappear soon. The half-life, denoted T1/2, is the time it takes for half of the original radioactive nuclei to decay. Mathematically, half-life equals natural logarithm of 2 divided by lambda, the decay constant we just met. It's like a kitchen timer telling you when half the popcorn has popped. Then, there's the mean life, symbolized by the Greek letter tau, representing the average time a nucleus survives before it decays. It's simply 1 divided by lambda. This links the decay constant directly to the lifespan expectation of a nucleus. From the exponential decay law n of t equals n naught times e to minus lambda t, we see that a shorter mean life implies faster decay, or a bigger lambda, like impatient atoms eager to change. Both half-life and mean life are intrinsic to the nuclei themselves. They don't care how many atoms you start with or the conditions around them. They're like a secret code written into the nucleus DNA. Imagine a graph showing the exponential decay curve with markings where half-life and mean life fall. We see half the atoms left at the half-life point and the mean life marked as the average stretch that any individual atom is likely to last. So, half-life and mean life help us quantify the ticking clock of radioactivity in understandable time scales. Now let's put a number on the action, how often those radioactive nuclei actually decay in a given time. Here's a light one. Why did the radioactive source go to school? To improve its activity. Activity, denoted A, is defined as the decay rate of nuclei at any time t. It equals lambda times n, the number of undecayed nuclei. The unit is the becquerel, abbreviated as BQ, meaning 1 decay per second. So, 1 becquerel corresponds to 1 nucleus making its grand exit every second. There's also the older, bigger unit called the curie, named after Marie Curie. 1 curie equals 3.7 times 10 to the power of 10 becquerels. Huge, isn't it? This unit helps measure the massive activities found in nuclear reactors and medical sources. Activity decreases exponentially over time, like the number of undecayed nuclei, following A of t equals a naught times e to the power of minus lambda t, where a naught is the initial activity. So activity and number of atoms go hand in hand, both dropping with the same decay constant. Measuring activity is super important in many fields, from tracking nuclear reactions and radiation safety in hospitals to determining the age of archaeological artifacts by carbon dating. Picture the plot of activity versus time sloping down exponentially, matching the decay curve we saw earlier but now telling us about how many nuclei are going off per second. So activity helps us keep score of the invisible nuclear party happening all the time around us. Let's see all this theory put to work with a classic example, carbon dating. Here's a joke to keep us going. Why don't archaeologists get stressed? Because they always find time to relax, literally, using radioactive clocks. Imagine you find a wooden sample containing only 25% of its original carbon-14 left. Given carbon-14's half-life of 5,730 years, how old is that sample? First, we use our decay law, n equals a naught times e to the minus lambda t, with lambda equal to natural logarithm of 2 divided by half-life. Substituting these values, the ratio n over n naught is 0.25, meaning only 1/4 remains. Setting up the equation gives e to the minus lambda t equals 0.25. Taking natural logarithms of both sides leads to minus lambda t equals natural logarithm of 0.25, which equals about minus 1.386. Solving for t, we get t equals 1.386 divided by lambda, which is 1.386 times half-life over natural logarithm 2. Plugging in 5730 years gives approximately 11,460 years. This age makes perfect sense for things like ancient wooden artifacts or fossils, showing how carbon dating lets us peek into the distant past. Picture the decay chart with percentage left on vertical axis and years on horizontal, with markers at 100%, 50%, 25%, showing the exponential drop and where our sample falls. So, carbon dating is a beautiful real-life application of radioactive decay laws, turning nuclear physics into a time machine. Alright, superstars, let's wrap up today's radioactivity lesson with a quick summary. The number of undecayed nuclei over time is given by n of t equals initial number n naught times e to the minus lambda t, and activity A of t equals lambda times n of t, which equals initial activity a naught times e to the minus lambda t. The half-life, t1/2, is natural logarithm 2 over lambda, while mean life tau equals 1 over lambda. We learned about alpha decay, where the nucleus loses to protons and to neutrons as an alpha particle, beta minus decay, involving neutron turning into proton plus electron and an antineutrino, and gamma decay, where an excited nucleus emits a photon gamma without changing its atomic or mass number. The key takeaway is that radioactivity is intrinsic and random, with decay rates governed by an exponential law tied to the decay constant lambda. Half-life and mean life give us time scales to understand the statistical nature of decay. Activity tells us how fast atoms disintegrate, playing crucial roles in dating techniques, nuclear medicine, and various nuclear technologies. That's your radioactivity recipe: spontaneous nuclear transformation, a cosmic game of chance governed by neat mathematical laws. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.